Now that we have talked about the equation of simple harmonic motion, we can look at forces and simple harmonic motion. The motion of an object is determined by the forces acting on it. So when an object moves with a simple harmonic motion, the forces acting on it are causing the object to move. And simple harmonic motion can be described where the acceleration is given by a is equal to minus omega squared x, where omega is a reference of its right sound. Omega is equal to 2 pi f. And we know that the resultant force on any object causes an acceleration given by f is equal to ma. Okay, so we can equate these together to get f is equal to mass times minus omega squared x, because this is the acceleration, which gives the equation f is equal to minus m omega squared x, where m is the mass of the object and F is the resultant force. So forces acting on the object must therefore give a resultant force, which is, and these are the two rules that it always follows, always towards equilibrium. And it's always proportional to displacement. Proportional to displacement. Okay, now we're going to look at motion of the mass on a spring when it's oscillating. We're going to look at three different situations of the mass on a spring. When the spring is at rest, when it's been pulled down, and when it's released and it's gone up. At this position we got tension pulling on the mass and weight coming down. Because it's in equilibrium, there's no resultant force, so T is equal to its weight. Tension is equal to weight. On this one we have tension pulling up plus kx. This is the spring constant times by extension, and this is Hooke's law. Hooke's law, where force is equal to kx, and we have weight pulling down. So the resultant force is going to be T plus kx minus w. Since the resultant force F is equal to kx upwards is going to equal T plus kx minus w. And this is the equation for the spring when it's been pulled down by the mass. And when it's gone up, let me use a different color, this would be x. It would be tension minus kx because it's going up, and weight. So it would be T minus kx minus w is equal to F. And since we take up as positive and down as negative, the resultant force would be negative. So T minus kx minus w is equal to minus kx upwards. Summarizing, this shows that the resultant force on the mass is directly proportional to displacement, but in opposite direction to displacement. When the mass goes up, the resultant force is downwards, and when the mass goes down, the resultant force is upwards. Damped oscillations are oscillations where the amplitude becomes smaller and smaller. There are three main types of damping, one being light damping. This is where the period remains the same and the amplitude slowly dies down. An example of a graph would be something like this. The amplitude slowly dies down. As you can see, the period remains the same, but it's the amplitude that slowly dies down. And an example of this would be someone on a swing. As you can see, the oscillations start off, and with no driver frequency, it slowly dies down. The amplitude becomes smaller and smaller until eventually it will come to a stop. As you can see, it eventually came to a stop. And this can be explained because of the friction in the chain and the metal bar that's holding it. The metal bar is rubbing around against the hinge, slowing the amplitude and making it stop eventually. Another example of damping is heavy damping. Heavy damping. There are no oscillations in this, and the body moves slowly back to its equilibrium. So an example of a graph of this would be something like that. X here and T there. And the final one is critical damping. And if a system, when displaced and released, returns to its equilibrium without overshooting and in the shortest possible time, it is said to be critically damped, and a graph would look something like this. This would be X and T. X and T over here as well. If you think about it, in practice, a simple pendulum gives an example of damped oscillations, although it will take a lot of cycles to stop. In this instance, it is because of friction due to air resistance. A practical use of damping would be in car suspension. Otherwise, when you go over a bump, you'll be thrown up and down until the oscillations died away slowly.